Alright, ladies and gentlemen, welcome to the Copper Cycle Lab. Today we're going to talk a little bit about what you experienced and saw in the lab. First thing I want to talk about is, in the lab, what happened? What happened? So, this time please think about what you saw and what you wonder about. In this lab you saw a number of different observations. Some of the things you may have wondered about include what happened? Why did the solution turn blue? Where did the copper go? So we're going to look at what happened, some of the reasons why this happened, and what you saw, and how that proves what you observed in this experiment. We're going to be looking at copper, and at the beginning you may have had copper, and at the end we're going to look at what you have at the end. So we saw copper only in the first and last steps of today's lab. Where do you think it went the rest of the time? Pause the video. Write down what you think. Be specific. Now, with your answers, you may have thought of the copper doing something, the copper changing, the copper going somewhere. Our observations show it was there at the beginning and it was there at the end. So what happened in the middle? To look at this, we're going to look about what goes around comes around, the law of conservation of matter. So what happened in the very first step when copper powder in the copper cycle experiment, when it was mixed with nitric acid? We're going to look at what was observed by the people in your group that went back to the hood to do that in this short video. This here is a 1969 copper penny, and concentrated nitric acid is being added to the penny. As it is added, you see a brown gas being produced, and the solution is kind of a greenish, not so greenish, more bluish greenish color. From our observations in lab 17, we might be able to identify what is that bluish greenish solution. What could it be? You also see bubbles forming. What could those bubbles be? And that brown gas is, we already know, is nitrogen dioxide. That's why we had to do this experiment in the hood. This particular reaction, as you can see, produces a large amount of brown gas. The question still remains is, well, what happened to our copper? Our copper that was placed in our solution, unlike this penny, what happened to the copper powder? So, possible hypotheses, what do you think? First of all, one thing, copper is a brownish color. What was brownish colored in that demonstration and in the lab? The gas was brownish colored. So that's one option. The copper could have gone to the gas. What's another option? Well, another option is the copper, if it doesn't go to the gas, well, maybe it could have gone to the liquid. So we had solid copper that was brownish color, we had a brownish colored gas, and a blue colored liquid, or bluish colored liquid, kind of green at first and then it turned blue. So the question is, where did that copper go? Where did the copper go and how do we know? So to look at this, we're going to look at what the copper was being added to, the nitric acid, and see if we can figure out or deduce based on our data from the previous lesson, lesson number 6, looking at our list. So you want to take that out, your list of all the substances we made observations about, their formulas, what they look like. From this, we're going to see what happens to elements in a chemical change. You'll be able to explain what the product of a chemical reaction depends on what was present at the time of reaction, and also that matter cannot be created or destroyed in a chemical reaction. So the first step of the reaction was that we had colorless nitric acid. It was being added to solid orange-brown copper powder. This resulted in a blue-green solution, brown gas, and liquid water. So this is a word sentence describing what we saw happening in the hood. So the first thing is the nitric acid. Okay, looking at our lesson number 6, we look up nitric acid. We see nitric acid's formula is HNO3AQ. And it's being added with an extra D, of course, just for fun, to the orange-brown copper powder, which has the formula Cu. Now, when these two are added together, it says results in a blue-green solution. So the question is, well, what's the blue-green solution? What is that? We know it's a bluish-greenish color. So what are our options? So one option you might have seen is we have on our list copper sulfate is one option. Another option is copper nitrate. And a third option is copper hydroxide. And maybe even copper hydroxide, depending on the color we got. So we have 4 different options. Now, to figure this out, just need to use a little bit of deduction, and we look here at the HNO3 and the Cu. These are all the things we start with. Okay? If we look at all the things we start with, what we end up with has to include some of those things. One of the products here is the brown gas. The brown gas, we're told, has the formula NO2. It's a little more difficult to predict why it's NO2, and we'll look into that more when we get more into in-depth chemical equations. In this sentence here, we know it's NO2. We're also told that water is produced. So we got H, we got our O, we got an N, we got an O. What we're missing here is definitely the Cu. The copper is not here in what we result. So either the copper disappeared because it's not in the brown gas, it's not in the water, or it's in the bluish-greenish solution. And if we look at all of our solutions here, all of them have copper in them. Now, could it be copper sulfate? Is there an S up here? No S. Could it be copper nitrate? There's an NO3, seems to make sense. Copper hydroxide? Maybe if all the N's went over there, but where'd the hydroxide come from? Well, there's an O, there's an H, maybe. So it could be either of those things. However, the bluish-greenish solution looks most like copper sulfate or copper nitrate. We know it can't be the copper sulfate, so the logical choice would be the copper nitrate. This here is called a chemical sentence. In the copper cycle, we started out with our copper powder, Cu. We added the nitric acid, and NO2 was produced. What we had left over in the solution was the copper nitrate, CuNO3 aqueous. The next step, it changed again, and we added sodium hydroxide. When we added sodium hydroxide, that formed a compound, for most of you, that was known as copper hydroxide. After we heated it up, it changed colors from a bluish lumpy stuff to a brownish black goop, for most of you. Few of you actually in this step got a bluish colored goop, this solid. And we'll try to explain why that could be. Added sulfuric acid to it and it turned light blue again, which was the copper sulfate. We added zinc to it and there was a huge change where the copper sulfate, the solution, turned clear, or almost clear, and we got the copper powder again at the end, even though it was wet. Looked a little bit different, but it was still that brownish copper color, and if we tested it and dried it, it would be the same material, same element. From this activity, we could prove that copper was not destroyed by measuring the mass of the copper powder at the beginning and the end of the experiment. So we can look at the masses we had at the beginning of the experiment, and we can look at the mass at the end of the experiment. This would show that copper was not destroyed. However, this does not necessarily prove, this doesn't prove what's called the law of conservation of mass. This law of conservation of mass is a law that states that mass cannot be gained or lost in a chemical reaction. Matter cannot be created or destroyed. In this lab, we can look at the fact that copper is known as an element. Evidence that it's an element is because of, one, the symbol. Second of all, because it is pure, just one substance, it's an element. It was not destroyed, even though it was mixed with many different things. But in the first step we had the copper, and in the last step we had the copper again. If we took that copper product we produced and we added nitric acid to it, we could make our copper nitrate again and go through the whole process again. Now, the mass of the copper initially, is it going to be equal to the mass of the copper at the end? If it is equal, that means that the mass before equals the mass after. However, did we have every single bit of copper at the end that we had at the beginning? Well, probably not. You might have even noticed the brownish blackish stuff we made was on the filter paper. And because it was on the filter paper, we actually threw some of that away. Could it have contained more copper in there? That is what we would say would be a source of error. This is why we didn't get the same mass before and after. Now, the law of conservation of mass states that the mass cannot be gained or lost in a chemical reaction, and matter cannot be created or destroyed. No matter what was done to the copper, it was not broken down any further. We were able to track the copper through all of its transformation using symbols for the element. At the end of the experiment, the copper was returned to the form we started with, solid copper. The experiment provides evidence that elements cannot be broken down or destroyed. Now, little amounts of copper were lost along the way. This could have been because of spills or measurement errors or the copper getting stuck on filter paper or even in the beaker. We had to clean up a little bit. Nevertheless, mass is still conserved. Even if the original copper didn't end up at the beaker at the end, it exists somewhere. Now, in our penny activity, the observations in this copper cycle lab prove evidence that the golden penny is not gold. If the golden penny were gold, it would have to have had gold somewhere in it. We had had copper in it, we added zinc to it, we had sodium hydroxide, and none of these are the element gold. So that means our golden penny has to be some mixture of the copper and the zinc. If gold is an element, then we probably would not be able to convert copper into gold by reactions similar to those carried out in the copper cycle lab, because elements cannot be created or destroyed by chemical means. Now, looking at the reaction, the first reaction we saw we did together here. This is known as a chemical sentence. Nitric acid plus copper makes copper nitrate, water, and NO2. In the second step, we took copper nitrate, which was our product, and we added sodium hydroxide to it. When they were added together, it produced a compound with copper and hydroxide and sodium and nitrate. Now, how do we know that that is what happened? Well, if we look at the copper and the hydroxide, the copper is written first, the hydroxide is written second. Hydroxides always seem to be written first, copper seems to be written second. So the copper nitrate attaches to the sodium hydroxide and they switch. The nitrate attaches to the sodium, so to speak, and the copper definitely attaches to the hydroxide. The reason we know this is copper hydroxide is because it forms a blue solid, kind of gloopy stuff, more like a lava lamp in the copper hydroxide. The sodium hydroxide is clear and colorless, so that's the solution we see. The copper nitrate solution was blue, it goes to a blue gloopy stuff with a clear colorless solution, and sodium and nitrate are the one thing that's left over, so we put them in the second aqueous solution. Then once we made that copper hydroxide, we heated it up. Now if you heat up something that has a solution, it's got copper hydroxide, what did you notice coming off of the beaker when you heated it? Some of you may have seen that the substance in the beaker changed color, but there was also some steam coming off. Steam is liquid water that is condensing because the warm gaseous water hits the cold air and condenses into little droplets. The copper hydroxide, when it's heated, you're removing water. Now there's already water in solution, but as you continue to heat it, you start removing some water from the copper hydroxide, the Cu parentheses OH2. This is because the CuOH2 has one O, one O, one H, one H. If you remove one water from that, you're left over with just CuO, and that's the compound, the CuO solid. The CuO solid is what normally occurs, because CuO solid is that brownish, blackish colored substance. However, some of you may have gotten a light blue substance. This is copper hydroxide, and the reason copper hydroxide might form is there was more hydrogens floating around in solution. This could have been because of extra nitric acid, but this sometimes happens upon heating. The product, whether it's copper hydroxide, CuOH, or copper oxide, CuO, reacts with sulfuric acid. The copper, and it produces a blue solution. The copper and the sulfate combine and the H2O connect, producing copper sulfate and liquid water. After the copper sulfate is formed, that's the light blue color we have, we added zinc to it. We stirred it and stirred it. We saw some bubbling occurring, some reactions occurring, and possibly some gas produced. And the copper sulfate bluish colored solution changed to a clear color. And what we ended up with at the end was a brown solid, which was our copper. So you can see here what is happening in this step is our copper and our zinc are switching places, so to speak, and the zinc is going into solution and the copper is coming out of solution. In this particular last step, it's possible that some of you actually got a bluish colored solution. This here would be referred to as a source of error. If you had more copper sulfate than zinc, more of this than you needed, you would end up with some extra copper sulfate at the end. That would make the entire aqueous solution bluish colored. If you had more zinc than copper sulfate, your solution would be clear, but you'd also have some zinc metal mixed in with your copper. And so you could actually get a result where the copper is contaminated with zinc and the mass of this copper substance, what you thought was copper, would be greater than what you originally started with. However, most people, when they do this experiment, see it's still a little bit blue. Some of you may have even seen that in the lab. So if you had extra copper sulfate, if you have excess, then the solution would increase in its bluish color. If you had excess zinc, you would have extra zinc left over, and that would be another solid along with the copper. So this is a set of all the equations that we could see for the 5 steps in the copper cycle lab. In our lab format, one of the things we will look at is the sources of error. We talked about this a little bit, and there is a particular format for sources of error. A source of error always has a logical statement. If something occurs, then something will either decrease or increase. So it's making a judgment based on not what did happen necessarily, but what could have happened or what in the experiment may have affected the results. So in this particular case, if less than 0.1 gram of zinc was added, then the final solution would increase its bluish color. That's the source of error. Then the next thing you write is a because statement, or why did this happen? And again, this is sometimes a prediction of why you think it happened. So this occurs because the amount of zinc in this particular case was not enough to transfer the copper sulfate into copper solid. Now that's again a prediction of why you think that happened. The important thing is noticing that there was an increase in its bluish color. This is your first source of error that will go in your lab report. You just need to come up with a second source of error. It must be different than this original source of error. Now, when you are typing your lab in your computer, one thing that needs to be done is making a subscript with Microsoft Word. So when you're typing in some of these chemical sentences using the formulas, you're going to want to use the following trick to help you type it into Microsoft Word. The first thing is if you want to do a formula, for example, if you want to do silver nitrate, which you see on this page, what you do is you type in AgNO3. Then you highlight the 3 and you press Control and plus, and it will make it small. That's how you type in AgNO3. And the second one you'll notice here, there's an arrow here. So the first one, how to draw that, is the Control plus and highlight. The second one, how to do the arrow, looks a little bit like this. So all you do is on Microsoft Word, you type in a dash dash and then a greater than sign, and it makes the arrow for you. So I'm just typing this into PowerPoint dash dash arrow and it's appearing. You can even go the opposite direction. There's my backwards dash dash, and it makes the arrow there if you wanted to go a reverse reaction, which we won't be doing for a while, so we'll make that disappear real quick. So this is how to make a subscript with Word, and this is how you're going to help write up your lab write-up. To wrap up what we know about elements, what happens to elements in a chemical change? First of all, elemental copper can be transformed through chemical reactions, then recovered. We can represent elements with symbols and keep track of them during chemical reactions by symbols and compounds with symbols. Elements combine or recombine but are not created or destroyed in chemical reactions. At this time, I'd like you to check in and answer the following question on your own sheet of paper and bring this to class tomorrow. That's it for the first YouTube video from the Copper Cycle Lab, We will see you tomorrow. I hope you have a good night.